In this video, we'll look at parametric equations where we have non-uniformly varying quantities. If we look at our equation here, we have x is a linear equation, whereas y is in fact quadratic. So if we were to work out some points and plot them on a Cartesian plane, if we were to begin with t equals 0, we've got 0 plus 1, we end up with 1 as the x value initially. And if we were to let t equals 0 in y, we end up with 3. So our first point is 1, 3. Next point, if t equals 1, we'll get 2 plus 1 is 3, and we'll get 6 for the y value. And if we make those substitutions, we end up with these values. If we were to graph them, we end up with a curve. Notice that given x is linear, if we were to move between t equals 0 and t equals 1, there is a shift of 2 squares here, 2 units, and between t equals 1 and t equals 2 is a constant change. We have moved, once again, 2 units. So each time the gap from here to here remains the same because x is in fact going to remain constant. As opposed to the y values, the shift from this value to this value here is 3 units. From here to here is 1 unit. Then from here back to here we're down 1 and we're down 3. So the y values are changing in varying amounts as opposed to x, which is going to remain constant. And if we use our software, we can graph the same function. So here's my x expression, which was a linear, and here's my quadratic for y, and we can plot those beginning at t equals 0, t equals 1, etc. Now, if we were to look at x and y were both linear expressions, then we can work out the velocity vector by working out x dash and y dash of t. So we can work out x dash here is going to be -3, and we can work out y dash from here, we end up with 2. So my velocity vector is the vector -3, 2. Now, in order to work out the speed, we would square the 3, we would square the 2 and add them together. So we'd in fact end up with 9 plus 4, we end up with √13 as my speed. Also notice that we can work out the speed another way by working out the square root of the dot product. The dot product of this vector would be 3 times 3 and 2 times 2, add them together, which gives us the same result we have here. So that's another way we can express the speed of our motion. So now let's look at our non-uniformly varying quantities. So once again, x is linear, y is quadratic. If we were to work out the values for x dash and y dash, x dash of t is going to equal 2, and y dash of t, differentiate this, we'll get minus 2t plus 4. And therefore my velocity vector is as written here. So if we were to work out the speed at different times, if t equals 0, we end up with x dash remains 2. If we were to work out when t equals 0, the y dash value will be 4. And the speed there would be 2 squared plus 4 squared. If I worked out any other value of x dash of t, this value would not change. So it's always going to be 2. But the y dash values will change. If t equals 0, I'm going to get 4. Sorry, yes, I got 4 there. If t equals 1, however, I've got 4 take 2, which is 2. If I let t equal 2, I'll get 4 take 4, which is 0. So these values will change. And therefore, each time I work out the speed, I'm going to square this value, square that, add them together. I'm going to get different results because this value will change depending on what t is equal to. and therefore my speed is not going to be constant. Now, if we were to plot the path of this motion, here's our curve once again, and here we've drawn in the velocity vectors. So when t equals 0, we're at this point here, but my velocity vector is 2, 4. So from here, my x step is 2, my y step is 4. So there's my velocity vector, and that'll be a tangent at that point there. When t equals 1, we're at this point here. Velocity vector is 2, 2. So 2 across and 2 up. And there is my tangential vector, a tangent to the curve at that point of contact. So following up from that idea of the vector being a tangent at that point, we can actually work out the slope of the function at a point on the curve. So if we were to work out y dash divided by x dash, well, y dash is the change in y with respect to t, so dy by dt, and x dash is dx by dt. Now, using the chain rule, remember these aren't fractions, but they in fact function as fractions. We have dy by dt and t by dx, which simplifies to dy by dx. So dy by dx, which is the gradient of the curve, can in fact be found by working out y dash on x dash. So by way of an example, if I had x and y were these functions here, if I found my value for x dash of t, I get -2, and y dash is 2t. So if I were to work out the y by dx using this expression here, I'll get 2t divided by -2, which is -t. If we were to write this pair of equations in Cartesian form, I'm going to rearrange this first one to get t as the subject and substitute that into the y function. And then if I were to expand, then if I were to differentiate this here, I'd end up with this expression. So -6 plus 2x on 4, dividing everything by 2 here, we get the same result because that is in fact the same as t. In fact, it's -t. So -t is the value we got here for dy by dx. So an example problem here, we have once again a linear expression for x, a quadratic for y. So this would be non-uniformly varying quantities. This represents the flight of an arrow fired by an archer in a tree, and y equals 0, it's ground level, distance in meters, time is in seconds. So how high in the tree was the archer when he fired the arrow? So that'll be at the start when t is equal to 0. So if we were to work out the y value, that would be our height. So we end up with 7 meters up the tree. All right, so what was the total time of flight? Well, the arrow will land at the ground when y once again is equal to 0. So if I let yt equal 0, we end up with a quadratic equation which can be solved using quadratic formula or the graphing calculator. So we end up with 5.95 seconds of flight. How far did the arrow fly horizontally? Well, the arrow was fired at t equals 0, so therefore I need to work out where I started, and x is the horizontal displacement. So if I were to let t equals 0, I'll get 2, and then it lands at 5.95 seconds, so therefore I need to work out what x of 5.95 is equal to. So once I do that, I've got these two distances. I then subtract the two from each other to work out the distance travelled. Part D, what was the maximum height reached by the arrow? So once again, the height is determined by the y component. So that is in fact a quadratic, and therefore if I were to work out when y dash of t is equal to 0, that should give me my result. So if I differentiate that, I'll get 28 take 9.8 t equals 0. So we end up with t equals 2.857. Therefore, work out the height by substituting t in the y expression, and we end up with our maximum height. Right, part E, finding the velocity vector for the arrow. So once again, x dash and y dash for the x and y components. So x dash will be 25 and y dash will be 28, take 9.8 t. And once again, the speed of the arrow will change because this value will be different each time we change the value of t, whereas that value of x remains constant. So if we were to work out the speed initially, so we have t equals 0, we can work out the velocity by letting t equal 0 in our velocity vector. So 25, 28 will be our values, and the speed therefore 25 squared plus 28 squared square rooted, we get 37.5 meters per second. Right, part 2 of question F, after 4 seconds, we would need to let t equal 4. Once again, in here we'll get 25 for the x component and the y value negative 11.2, square each, add them up, and take the square root. We've got our speed. Last part of the question, at what angle was the arrow fired? So the arrow was fired at t equals 0, so we have worked out previously our velocity vector is 25, 28, and therefore the angle the arrow was fired, we can draw a right angle triangle. There is the velocity vector there. So 25 for the x component, 28 for the y component, and the angle can be found using basic trig. So tan of theta is 28 on 5, and we can work out the value of the angle, and therefore that is the angle fired above the horizontal. Part 2 here, we want the angle the arrow is at when it strikes the ground. So we know that the time it takes, it was 5.954. So we let 5.954 replace t in this expression for our velocity vector. We would then draw our velocity vector. So x component is 25, y component is, we're going down, so negative 30. So therefore, to work out the angle here, we would do the tan of theta is equal to the positive length here is 30.4 divided by 25. That gives us the acute angle here, same as that angle down there. So the angle 50.5 degrees.